We won the flame challenge! Hey crazies, in our first video on black holes, we covered the basics. What are they? How are they made? What do we measure about them? And I said this: they're massive black balls of death. But only if you get too close. And that got me thinking, what would it be like to fall into a black hole? That actually depends on your point of view and the size of the black hole. First, let's revisit a couple things. Black holes have two basic parts. There's a singularity where space-time curvature is infinite, and an event horizon where gravitational time dilation is infinite. The size of that horizon is the size of the black hole, which depends on its mass. More mass makes for a bigger black hole, but still much smaller than you're probably thinking. If you're falling toward a black hole, the first thing you have to worry about is tidal forces. See, the human body can only accelerate so much before bad things start to happen. We can handle a lot if it's short and temporary. Falling into a black hole can be short, but it's nowhere near temporary. Our limits for continuous exposure are much lower. Somewhere between 4 and 6 Gs, you pass out. Somewhere between 10 and 14 Gs, you just die. Somewhere between 30 and 40 Gs, your body gets ripped apart. This is why humans are a major limiting factor in space travel, but it's also an issue near black holes. Space-time can get really stretched. If I let an expendable clone fall toward a black hole, then space-time will try to stretch him too. If space-time stretches enough, he'll get ripped into a thin piece of flesh. It's called spaghettification, and it's not a good time. But we can actually avoid it if we choose the right black hole. The bigger the black hole, the more gradual the stretch. 100,000 solar masses should be more than enough to keep my clone conscious all the way in. Okay, so we've got a supermassive black hole to work with. Let's say I'm on my space station at a safe distance. As the clone approaches the event horizon, he redshifts. Eventually, I have to watch him from infrared, and then microwave, and then radio, and into oblivion. But I never see him cross the horizon. Ever? Remember, the closer you get to a source of gravity, the slower time goes. It's called gravitational time dilation. The event horizon is a place of infinite time dilation, so it would take an infinite amount of time for my clone to cross it. But the clone has a very different story to tell. As he approaches the event horizon, he would see my time speed up. But nothing all that interesting happens for him. Inside the event horizon, things get super weird. All space-time paths point toward the singularity. Frontline physics alert. What is this? Oh! Frontline physics alert. Almost anything said about black hole singularities is merely a hypothesis, since there has been no experimental verification of any kind. Many of the details are subject to possibly significant change in the future. Was that really necessary? Where was I again? Oh, right. Toward the singularity. If I'm standing in a grassy field, I could walk this way, or that way, or even this way, all of which would take me to different places. But if this grassy field were inside of a black hole, no matter which way I face, I'm facing the singularity. Of course, all the light is directed that way too, so it would just look black. Of course, none of the events beyond the horizon even take place in our universe, so did it even happen? What do you think? Do the events inside the horizon actually happen? Let's continue this conversation in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to see more science like this. And until next time, remember, it's okay to be a little crazy. The last video was on gravitational waves. Comment response time! Kevin Suarez was amazed that LIGO had gotten switched on just in time to witness the black hole merger. Yes, that does seem like we're pretty lucky, but we're actually not. With the enhanced range, we actually expected to see mergers pretty frequently. And in the months between that detection and the announcement, we've already seen several more. Links in the doobly-doo. Moses asked about the number of values needed to describe the curvature of spacetime. That actually came from the Riemann curvature tensor. Technically, it has 256 components in 4 dimensions, but a lot of them are the same. There are at most 20 independent components in that tensor. If the spacetime is simple, it could be less, but that's super mathy stuff. Speaking of mathy stuff, Matthew, see what I did there? Such a dork. Matthew was disappointed I didn't go into the mathy details. But to be honest, I'm pretty disappointed when I have to leave some of the mathy stuff out. It's just tough to convey in a video without boring people to death or scaring them away. I do have some good ideas on how I might make it work, but that's going to take a lot more time and probably a little help to make a reality. There are things that I just can't do by myself. Nobody's felt like I did Voltron a disservice by only showing the super robot form. You're absolutely right. There's no excuse. I stand before you in shame. And Pablo, you're very welcome for the credit. It's the least I could do. That graphic of the universe is amazing. Keep up the great work. That's it on gravitational waves for now. Maybe this way of answering comments will stimulate some conversation. Thanks for watching.